So today, we're going to dive into how one of the toughest, tiniest creatures on Earth is handing scientists the keys to solve some of the biggest problems in human health. And the crazy part is, the answers aren't coming from some high-tech lab, but from a microscopic marvel of evolution. Okay, just think about this for a second. What if, at the scene of a terrible accident or a wound on the battlefield, you could just hit a pause button on biology? Stop the damage in its tracks, halt the inflammation, and buy precious, life-saving time. I know, it sounds like something straight out of sci-fi, but the secret might just be hiding in plain sight. These right here, these are some of the huge mountains we're trying to climb in modern medicine. How do we protect healthy tissue when we're blasting a tumor with radiation? How do we extend that critical golden hour for a trauma victim? How do we get fragile, life-saving vaccines to every corner of the globe? And how do we keep a donated organ viable for just a little bit longer? They're all monumental challenges. And what if I told you the solution to all of them might come from the same, tiny, unlikely place? All right, so who is this hero? Well, it's not a brilliant scientist or a new AI. It's this tiny little creature, a microscopic invertebrate that people affectionately call the water bear. So here it is, the tardigrade. You're looking at something less than a millimeter long. I mean, you can barely even see it. But this little guy, its ability to survive is just legendary. We are talking about an organism that can handle conditions that would kill almost any other living thing, especially us, in an instant. Okay, let's try to wrap our heads around this number. The lethal dose of radiation for a human is somewhere around 4 or 5 gray, or GY. Tardigrades can handle over 5,000. That is more than 1,000 times what would kill one of us, instantly. It's just an insane level of radiation resistance. And hey, it's not just radiation. You can basically cook them at temperatures way above boiling or freeze them to within a degree of absolute zero, the theoretical point where atoms pretty much stop moving. And then, when things get better, they just soak up some water and go on with their day, like nothing ever happened. Get this. Back in 2007, scientists strapped some of these guys to a satellite and sent them into space. They were exposed to the pure vacuum and the harsh, unfiltered radiation of orbit. And when they got back to Earth, many of them were just fine. They were revived and even went on to have babies. So we're not just talking about surviving, we're talking about thriving after enduring the most hostile environment imaginable. So you gotta be asking the same thing I was. How, right? How is any of this even possible for a complex animal? And the answer? Well, it's not magic. It's something even cooler. It's molecular engineering at its absolute finest, perfected over millions of years. So researchers have dug in, and they found that the secret sauce, if you will, is in its molecular toolkit. Specifically, it comes down to a set of proteins that are completely unique to the tardigrade. All right, let's break this down into two key players we're going to focus on. First up, you've got a protein called D-soup. Think of it like a tiny molecular bodyguard for its DNA. Then you've got this whole family of proteins, and the star player is one called CHAS. These are the guys that are basically the architects of suspended animation. All right, let's dig into that bodyguard first, because this is really where the story starts to get medically relevant for all of us. So, D-sup. The name stands for damage suppressor, and it does exactly what it says on the tin. It's what's known as an intrinsically disordered protein, which means, unlike most proteins, it doesn't have a fixed shape. It's flexible, almost like a liquid. And this lets it literally wrap itself around the cell's DNA, forming this protective physical cushion. But here's the thing. It's not just some simple shield. Its defense system is incredibly smart. It physically blocks the bad guys, these things called hydroxyl radicals that radiation creates, from ever reaching the DNA. But it does more. When you put D-sup into human cells, it also lowers the overall level of other damaging molecules, and it actually revs up the cell's own internal defense systems. It's like having a security guard who not only blocks the door, but also hits the alarm and gets the entire security team mobilized. Okay, so that's the bodyguard. Now, for what might be the craziest superpower of all. This is where we get back to that idea of hitting the pause button on life. It's a process called biostasis, and it's all run by that other family of proteins we mentioned, CAHS. The technical term is biostasis, and it's basically nature's ultimate survival hack. This isn't just hibernation or sleeping. It's a complete and totally reversible shutdown of pretty much everything. The tardigrade just turns itself off to wait out whatever storm is coming. So, how does it pull this off? Well, imagine the cell senses danger, like it's drying out. Instantly, these CHS proteins kick into gear. They start linking up, building this incredible network of tiny fibers. Pretty soon, this network turns the whole inside of the cell from a liquid into a protective gel. This process, it's called gelation. It just locks all the important machinery in place. Metabolism grinds to a halt, and the best part, as soon as the danger's gone, say, a drop of water comes along, the gel just dissolves, and the cell picks up right where it left off. Totally fine. One of the researchers working on this summed it up perfectly. He called it like freezing without the ice. You get all the protection of being frozen solid, but without any of the destructive ice crystals that would normally just shred a cell to pieces. It is a way smarter way to pause life. Okay, so let's recap. We have a protein that acts like a DNA bodyguard and another one that can hit a cellular pause button. This is where it gets really, really exciting because scientists aren't just watching this happen, they're actively figuring out how to give these superpowers to our own cells. So this really breaks down into two major paths for medical breakthroughs. You've got DSUP, the DNA shield, which is pointing towards safer cancer treatments and protecting organs. And then you have CNAHS, the biostasis expert, which could totally change trauma care and how we handle critical medicines. All right, let's talk application number 1, cancer. We all know radiation is a powerful tool against cancer, but it's always been a bit of a blunt instrument, right? It damages the healthy tissue right alongside the tumor. Well, this is where DSUP could be a hero. Studies are showing that if you give healthy human cells the DSUP protein, they get that same tardigrade level protection from radiation. And here is the absolutely crucial part. You can target this protection. You can protect the healthy cells in a patient's mouth, for example, preventing horrible side effects, but you leave the tumor vulnerable, so the radiation can still do its job. This isn't just a small improvement, this is a potential game changer for millions of patients. Okay, on to application number 2, and this one sounds like it's straight from a futuristic movie. A smarter Band-Aid. So you remember that gel that the CAHAS proteins make? Well, scientists are now creating hydrogels that do the exact same thing. The idea, which is part of a DARPA project, is that you could apply this gel right onto a major wound. It would seep into the cells and trigger that localized biostasis, essentially pausing the injury in its tracks. You're not just buying minutes, you're potentially extending that critical golden hour into many hours, maybe even days. Just think what that could mean for a soldier on the battlefield or someone in a rural car accident. All right. And for our third major application, we're tackling a massive global health problem that you might not even think about, the cold chain. So a lot of our most important medicines, things like vaccines or treatments for hemophilia, they're called biologics, and they are super fragile. They have to be kept refrigerated from the moment they're made to the moment they're used. And this cold chain is this huge, expensive, logistical nightmare, especially for getting medicine to places without steady power. And the tardigrade solution is just so elegant. It turns out if you just mix these Cas proteins in with the medicine and then dry the whole thing out, the proteins form that protective gel matrix right around the drug molecules themselves. Suddenly, you have a stable powder that doesn't need a fridge. You completely break the cold chain. This could mean getting life-saving treatments to literally everyone. Everyone. So, safer cancer treatments, a pause button for injuries, and a way to get medicine anywhere in the world. I mean, that's already revolutionary, right? But believe it or not, the story doesn't stop there. We are just scratching the surface. When you start thinking about it, the possibilities are just mind-blowing. That same DSUP protein, it could protect donor organs, giving them more time for transplants. It could shield astronauts from cosmic rays on a trip to Mars. We could even engineer crops with these proteins to survive massive droughts. And yeah, some scientists are even looking at how biostasis could give us clues to slow down aging itself. So what this all really comes down to is this. By studying this incredible little animal, we're not just looking at some weird curiosity, we're actually unlocking a whole new platform for medicine, one that could totally redefine how we treat disease, how we respond to trauma, maybe even how we age. And it's just an incredible reminder that sometimes the absolute biggest breakthroughs can come from the most unexpected and tiniest of places.